So we made it. Chapter 10, Section 5, Easy Graphing Square Root Functions. Our learning objectives for the section is to graph square root functions, easy, and to translate graphs of square root functions, easy. So our key concept is that, let me get my highlighter out so we can highlight it. A square root function is a function containing a square root. What? Crazy talk. Square root function has a square root. And the independent variable is in the radicand. Independent variables are usually our x, and it's inside the root. The parent function is y equals square root of x. So we are going to make a little t-chart of our x and y values. And once we do a couple, we can see what some smart variable decisions will be. So, all right, so when we go to graph a square root function, we should be smart about what we input into the function. The first two are pretty easy. When we put in 0, the square root of 0 is 0. So let's plot that point on our graph. That's right here. When we put in 1, square root of 1 is 1. So we plot that on our graph here. We put in 2. Square root of 2 is an irrational number. It's 1.41, all different. So I'm not going to put that point on my graph because I want more exact values. So let's think about this smartly. The best number to put into a square root function is a perfect square. So when you input values into a square root function, let's make sure they end up perfect squares. So we've got square root of 4 is 2. So we go over 4 up 2. Then we skip to 9 because 9 is our next perfect square. So we go square root of 9 is 3. So once we have those basic points, we draw a smooth curve along that line. My smooth curve just went south. And your square root functions are always going to be like that. I can't get my line to curve. Okay. Let's talk about the domain and range of these guys. Domain is your approved x values. And what's the restriction with square roots? What are we not allowed to do with square roots? What happens with square roots that will cause the zombie apocalypse? Cannot be negative. Thank you. So our x values underneath the square root cannot be negative. So when we look here at our sample question, what is the domain of y equals square root of negative 2x plus 5? So we want to know when negative 2x plus 5, actually let's go like this. We want negative 2x plus 5 to always be greater than or equal to 0. Because if it's less than 0, it's going to be negative, and that will cause the world to end. So we're going to solve this little equation, and once we do, we will have the domain. So when I subtract 5 from both sides, I get negative 2x greater than or equal to negative 5. And then I'm going to divide both sides by negative 2. And when you divide by a negative, it causes this inequality to switch. Negative 5 divided by negative 2 is positive 2.5. So this right here is our domain. X has to be less than or equal to 2.5. And just to illustrate the point, let's do a little XY table to see what happens. So if y equals the square root of negative 2x plus 5, I'm going to multiply by negative 2, add 5, and take the square root. So when I do that to 0, so in for x, I'm going to put 0. Negative 2 times 0 is 0. And 0 plus 5 is 5. And just so I can give you an accurate, the square root of 5 is 2.23. All right, then let's do 2. And negative 2 times 2 is negative 4. Negative 4 plus 5 is 1, and the square root of 1 is 1. All right, let's test this limit. It says we have to be less than or equal to 2.5, so let's go forward. Let's see what happens when we go above our domain. So we got negative 2 times 4, which is negative 8. And then I have negative 8 plus 5 is negative 3. And I cannot take the square root of a negative, so there is none. So that just illustrates why the domain cannot be bigger than 2.5. Otherwise, it's going to be negative. All right, I wanted to show you this problem so we can see how to use graphing in a real-world manner. On your paper, I want you to write this highlighted equation. Graph the function I equals 1/5 square root of p, which gives the current I in amperes for a certain circuit with p watts of power. When will the current exceed 2 amperes? So step number 1 was to make a table, and step number 2 was to plot the points. So once they did that, they saw that, because their goal was 2 amperes, they saw that when they plugged in 100, they got out 2 amperes. The current will exceed 2 amperes when the power is more than 100 watts. So we're going to do that problem. When will the current in problem 2 exceed 1.5 amperes? So we look at these values here. And we realize that 1.5 is in between 1.4 and 2. And that means our x values are going to be between 50 and 100. So let's make another t-chart. And let's put down our goal is 1.5. So my p-values have to be between 50 and 100. So let's give me some numbers that you think will get us to 1.5. Should we try 55?
Yeah.
Let's try 60. And then before, let's do those two before we decide how we want to, if we need more data points. All right, so let's get out our calculators. And we have the square root of 50 times 1/5. And that's equal to, oh, sorry. I want the square root of 55. Let's try that one. Times 1/5 equals 1.48, which does not exceed 1.5 yet. So let's try 60. So the square root of 60 times 1/5, and I get 1.54. So based on these numbers, what should our next value be that we should try? We're aiming for 1.5. 55 gave us 1.48, 60 gave us 1.54. What should we try? We're aiming for 1.5. All right, so let's try 57, and just in case 57 doesn't work out, let's try 56. So we have 1/5 times the square root of 57. Calculator says square root of 57 times 1/5 is a 1.509. That's a pretty good one. Just for fun, let's do 56. Doesn't hurt for us to have accurate data. $1.496. Okay, so I think reasonably we can say that A is equal, when will the current exceed 1.5 amperes? When the power is equal to 57 watts. And then it says, by how many times must you increase the power to double the current? So think about square root. Normally when we double things, we times it by 2. But we have to counterbalance the square root. So we're not only going to multiply by 2, but then we're going to square the 2 to counterbalance the square root. When I square 2, what do I get? 4. So let's multiply this guy by 4 and see if we can't get our current to double. So what's 100 times 4? 400. And let's see if this 2 becomes a 4. Let's see if it'll double. So if I take 400, I take the square root, and I multiply it by 1/5. My fingers are crossed that I'm going to get 4. And it does. So to counter the square root, I have to increase the power by 4 to double the current. All right, last topic. For any positive number h, graphing y equals the square root of x plus h translates the graph of y equals root x, which is the parent function, to the left h units. Graphing y equals square root of x minus h translates the graph of y equals square root of x to the right h units. of the story of translating graphs is that when your h value is on the outside, like it is here, it's going to move your parent function up or down. So I'm going to put the parent function on here, and then you guys can move it up or down with me. So I'm going to graph the parent function that we graphed together. Do not graph this because I'm going to move it. So when we are, if you remember from our t-chart, we're going to plug in 0, square root of 0 is 0. Plug in 1, square root of 1 is 1. And then we skip to 4 because 4 is a perfect square. Square root of 4 is 2. All right, and then we skip to 9. Square root of 9 is 3. So here is the parent function. Now, when we follow this rule right here, when h is on the outside, it moves it up or down. So I'm looking here, I have minus 3. So it's going to take this entire parent function and move it down, because it's negative, it's going to move it down 3 units. I guess we'll do it like this. So instead of starting at 0, it's going to start at negative 3. So go ahead and graph that parent function starting at negative 3 instead of 0. All right. And then we look at the other scenario when I have a value inside the radical. It moves it left or right. So when it's on the outside, it's easy. It'll move it up or down. When it's on the inside, it's opposite the sign. So if I have minus 3, it's going to move it to the right 3. If I have plus 3, it's going to move it left. So it always moves opposite to the sign when it's inside. So let me show you how that works again. I'll graph my parent function. Remember, it's 0, it's 1, 1, it's 4, 2, and it's 9, 3. So if you have your parent function, in this case, I'm going to move 3 units to the right. So we take our parent function, and we move it 3 units to the right. And that's all we gotta do.